I'm going to try and explain the geometry behind all of this now. So here's where I would start off if I were in class with you today. Here's an object, mass m, sitting on an inclined plane at some angle, some unknown angle, theta. And we know that the force of gravity is going to act straight down. Okay, so there's the force of gravity. It's mass times g acting straight down. Now we can break that force of gravity up into components, like we've been doing in the last two units, breaking up forces or vectors into components. One component is acting downslope. It's actually pulling the mass down, making it slide. And the other component is kind of pushing it into the surface. It's pressing it against the surface, right? It's creating a kind of like a normal, it's going to create a reactive normal force. Well, this angle in here is also theta. If we draw a right angle triangle here, right, this angle is theta. This angle is its complement, what adds up to give you 90 degrees. And this angle here is also the complement, right? So of this one here. So this has to be theta. You can stare at this for a while if you want. But if I draw this line all the way down here, I'm going to create three similar triangles. And the angle up here in the corner is the same as the angle here. Now, the way that works is this. The component that's touching the angle is the cosine one. The component that's not touching the angle is the sine one. That it always works like that. It doesn't matter how you rotate it, how it's oriented. It always comes out that way. So here, the component of gravity, the perpendicular to the slope component, is actually going to be mg cosine theta. And that means that the reactive normal force is going to equal mg cos theta. So here we'll have mg cos theta pulling into the board. That's what gravity's doing. And mg cos theta is going to resist. Now, the force of friction is always mu times the normal force. You might hopefully remember that from 2204. Well, we've already got an expression for the normal force. It's here, mg cos theta. So that means the force of friction is mu mg cos theta. That's what's acting upslope. Acting downslope is the sine component of mg. So mg sine theta. Now in the lab that I'm giving you, there's two different scenarios. One, the object is just sitting there on an inclined plane, and you want to calculate the force of static friction. And the way to do that is you get the angle at which it just starts to move. At that point, the force of static friction and the force of gravity acting down slope will equal each other, and you can calculate. The only unknown then is your mu, and you can calculate that. And then the other thing to do is to get the object sliding at uniform motion. And when you do that, the force of kinetic friction acting upslope and the force of gravity, the component of gravity acting downslope, will be equal to each other. And you can let those two things equal each other, and you can solve for the only unknown, which would be your coefficient of kinetic friction. So I'm posting these notes there for you to look at, but my explanation hopefully will help you out a bit. The main thing to get out of this is look at the geometry. Okay, so there's your theta, there's your theta. You kind of have to accept in your own mind that that's true. And then if you know that that's theta, then this component has to be the cosine one, and this component has to be the sine one. Okay, and there's no, you don't have to think about it anymore. It's like touching and not touching. It always works. So this is the kind of like the theory behind the calculations I want you to do for this investigation.